So Unit 8 is all about continuous distributions, and Unit 7 we talked about discrete. And so Unit 8 is finding probability with continuous distribution. So that's going to include two different types. We're going to look at uniform distributions. We're also going to look at normal distributions. But essentially, in continuous, the way that you find probability is just finding the area under the curve. So you could use some fancy calculus and find the integral and things like that, but we're going to make it really simple and just do it in the calculator. So consider we have a random variable. Remember, continuous includes anything that you measure. So it could be height, weight, volume, distance, time, anything like that is always going to be continuous. So the weight of a full-term newborn child, this would be continuous. And here is a histogram that shows the distribution of the weights of newborn babies, and those are represented in pounds. The area of the rectangle centered over 7 pounds represents the probability from 6.5 to 7.5. So since it's centered under the 7, it represents anything from 6.5 to 7.5 pounds. What is the sum of all of the areas of the triangles, or of the rectangles? So if it's all the probability, then I'm going to add up the areas. What should they equal? 1. Perfect. So now suppose that the weight is reported to be the nearest 0.1 pound. So instead of like 1 pound increments, I'm going to now split it into 0.1 pound increments. And what do you notice about this distribution?
It's more symmetrical. Or not more symmetrical.
It's curvier. Yeah, so imagine taking your rectangles and just shrinking them, making them really, really small. Like the increments are smaller, so it's more rounded. So when you're making your increments or your intervals smaller, it's actually creating a more rounded distribution. And this actually looks very similar to a normal distribution. Has a smoother appearance. So if weight is measured with greater and greater accuracy, the histogram approaches a smooth curve, and it looks more normal. And so it really is just dependent on your intervals and the increments in which you're measuring them. The shaded area represents 6 to 8. So if I found the area under that shaded curve, you would end up getting a decimal, and that would represent the probability that when you have a newborn baby, it's going to weigh between 6 and 8 pounds. And we call that a density curve. So the density curve really is just finding the area underneath that curve. And so any continuous distribution is called a density curve. It's what we'll refer to it as. And we call that function f of x the density function. But essentially all that we really need to know from this chapter is that when we're calculating probability, essentially what we're doing is finding the area under the curve. So most of the time we're going to be able to use our calculator to do so. There will be a few times where we actually have to use or do it by hand by looking at shapes like a rectangle or a triangle or different geometric shapes that we're finding the area under the curve. So properties of continuous probability. It's always going to be greater than 0, so your function will never dip below 0 because your y-axis is always represented by probability. So whatever your y-axis is, it's always going to be a number between 0 and 1. So if I were to draw my y-axis like this, it's going to start at 0 and it's going to end at 1. And it's probably never going to touch 1. But your curve will always be something like this, in between 0 and 1. So you'll always have a horizontal line at 0. You can never have a negative probability, so that's why it never dips below the horizontal axis. You might see like a multiple choice question that kind of talks about that. Maybe like a true, false, or something along those lines. And then the total area of the density curve does equal 1. So here's an example of a sort of density curve that you might see, and it's a piecewise function. So it says, let X denote the amount of gravel sold in tons during a randomly selected week at a particular sales facility. Suppose the density curve has a height above f of x above the value x, and then it gives me my constraints. So here's my piecewise function, and if it wanted you to graph that, it would look like this, where my y-intercept is at 2. It has a -2 slope. So here's my density curve. It's just a value between 0 and 1, and I could find anything between 0 and 1. I could find the area under that shaded curve. There we go. So then it's going to ask you questions about, it'll give you the density curve. Most of the time it gives you the drawing. If not, then it would give you the piecewise function. You'd have to just graph it. But it'll ask you questions about the probability. So it says, what is the probability that at most 1/2 ton of gravel is sold during the randomly selected week? So in that case, if it's at most 1/2, what does my probability statement look like? That x is what? Less than or equal to 1/2, because it says at most. So that means 1/2 is going to be my highest point. So based on this picture, I'm going to shade everything from 0 to 1/2. And I want to find the area of that shaded region. Now I don't have like a fancy calculator function to do that. I just have to use simple geometry. And so what kind of shape does this make? A trapezoid or a triangle and a rectangle. So you could do one of two things. You could either treat it like it's a trapezoid and use the formula for that, or you could treat it as a triangle and a rectangle and then just combine those. Basically, whatever you need to do, you might want to brush up on some of your geometry formulas. Like triangle, rectangle, trapezoid maybe. Yes.
Okay, how come the y-axis is over 1? I was confused.
Because it's a downward slope.
But I thought, or have we moved away from the probability?
The whole, like the area under that entire function is going to be equal to 1. So if I did this whole thing.
Yeah, I get you. Because there's 0.75 or 0.25 left. So
Right.
Okay.
So if I did 1/2 base times height, so 2 times 1, it would end up getting 1 whole. So the probability would be shaded under the curve about the interval from 0 to 0.5. This is the formula for a trapezoid, so you might want to write this down. I don't think it's on your, like the pop-up isn't on your slides. So you might want to write out to the side formulas I need to memorize. You don't have to memorize the trapezoid because you know you can combine rectangle and triangle if you want to do composites, or you can just memorize the trapezoid formula. Either one. One-half base times height, formula for a triangle. And then base times height is obviously the rectangle formula. So one thing you could do, and that's what the PowerPoint slide did, is it did 1 minus this rectangle or this triangle right here. Because we know that the whole triangle equals 1, so you could do 1 minus and then find whatever is left over. Another thing that I could do is the trapezoid formula, where I have height 1 and height 2, or base 1 and base 2, and then height of 0.5. 1 and 2. I could also split it up into a triangle and a rectangle. But I'm fairly confident in your geometry skills. You have made it this far, so a couple years ago. I think you can do this. So I'm not going to spend too much time going over that. What's the probability that exactly 1/2, what do you predict about this one?
50%.
Exactly 1/2? What's the area of a line? Because this is a line essentially, right? No, it's not infinity. It's 0.
Just kidding. Whoa. What? An area of of a line is 0?
How do we find the area of a line segment? We don't. It's 0. Because a line segment's is one-dimensional. So you don't have any height.
Is every exact is that right there?
So you'll never have like a PDF function in this. You'll never have exactly. So continuous is always measured on a range or an interval. And so therefore we'll never have a PDF, we'll never have an exactly. So anytime a question says what's the probability that exactly 0.5 or the baby weighs exactly 7 pounds, it will always be 0. So the word exactly in this unit will always be 0, because when you have a function like this, it's the x-axis is on a range.
No, the line makes sense, but I don't get the baby part. Like, baby, what's the probability that baby weighs exactly 7 pounds? How is that?
You have to give some sort of range of values. So you could say between 7 and 7.01 or something like that.
No,
You have to give,
Yes, they can.
It's impossible.
they can, but whenever you're finding the area under the curve, if the probability is on exactly a line, you end up getting 0 because you can't find the area under a curve if you don't have any range of values. So since a line segment has no area, the probability that exactly 1/2 ton sold is equal to 0. What is the probability that less than 1/2? How is that different than at most 1/2?
You do the 1 thing, 1 minus.
It's not. It's not any different.
It's not any different. So does the probability change whether 1/2 is included or not?
Nope.
No.
Exactly is 0.
So in this unit, or in continuous functions, less than and less than or equal to, or greater than or equal to, are the same. You're going to end up getting the same answer. So with continuous, whether it's 1/2 is included or not does not matter. Because if it equals 1/2, remember that probability is 0. So this is different than discrete, where in discrete it does change the probability if it's included or not. In continuous, it doesn't change the probability. So those are considered like unusual distributions, where you're essentially finding the area under the curve using geometry. So that's one section of this. There's 2 more sections I will talk about. Yes?
I'm still confused. It's like I'm still confused why it goes up to 2 and not 1.
Because the area under this entire triangle is equal to 1. So the only constraint of a continuous function is that the area under the curve is equal to 1.
Oh, okay.
So whatever is under the curve equals 1. So if I found the area of this whole triangle, it would equal 1.
Okay, that makes sense.
Okay. The next type is uniform distribution. So we had unusual, find the area under the curve. Uniform distribution, does anyone remember what that looks like, the shape of that?
Equal.
It's symmetrical, but they're all, it's the line, like they all are the same. So an example of a uniform distribution would be when you're rolling a dice, you expect that you would land on 1, 2, 3, 4, 5, and 6 an equal amount of times.
Heads and tails.
So heads and tails, that could be a uniform distribution. You expect that you end up getting the same amount of outcomes for each outcome. Like you get the same number for each one. You get the same number of 1s, 2s, 3s, 4, 5, and 6. Same number of heads and tails. So they're evenly distributed. Circle the word evenly, because a question, like a multiple choice question, may say that it's an even distribution. Those two mean the same thing. It looks like a rectangle, so all you're doing is taking the base times the height. How do you find the area of a rectangle? Base times height. Yay. This is the formula for the mean and the standard deviation
Of what? Uniform distribution.
of a uniform distribution. It actually gives you the variance. So I want you to write this. Mean and standard deviation. So square root it.
And this is on
On
the
the
formula
APTS,
sheet.
what do they give
This
us?
will be on the APTS.
Nope. They don't give you these.
What was the
So
formula?
we do have.
However, the mean makes sense. So A and B are the end points. of the distribution. So all you're doing is basically finding the center point, because when you have a rectangle, the mean or the average is always going to be in the middle. So you're just this is essentially just finding the averages of the endpoints. Endpoints meaning like your min and your max. And this is honestly, this is going to make more sense when we do an example, because these formulas may look kind of scary, but they're not. And then to find the standard deviation, all you're doing is taking the b minus a, which is essentially the same thing as your range squared over 12, and then square rooting it. And the reason why people have asked me in the past, like, why is it 12? Like, why is 12 a magic number? And there's this really long mathematical proof that I can send you if you're curious. I know a lot of you probably are. Okay, here's an example. So it says, suppose x is a continuous random variable defined as the amount of times. So that means it's continuous. Taken by a clerk to process a certain type of application form. Suppose x has a probability distribution with the density function. So it's giving me the function where the height is, it's a horizontal line. The height is 0.5 and the range is from 4 to 6. So I have a function that looks like this. And I normally will draw my vertical lines down like this. Another way that they could have asked you this, sometimes they only give you the range and they don't give you the height. So maybe they didn't give me any of this information right here. They just said that the smallest is 4, the minimum is 4, the max is 6. Then you could actually calculate the height by doing 1 over the range. Because you want the area under the curve to equal 1. So if you take base times height, it would be like saying, so if my range is 2, which would be my base, and my height is 1 over 2, that equals 1. So essentially, you sometimes have to come up with the height on your own. You're just doing that. Height is always 1 over the range. So I want you to write that in. They aren't always nice in giving you the height. So what is the probability that it takes more than 5.5 minutes to process the application form? So I'm just taking the area from 5.5 to 6. Base times height, what would my base be? 0.5. My height is 0.5. So this is pretty simple. The only difficult thing about this kind of question would be when they don't give you all of the, so they could just give you the range. Sometimes they could just give you the height and you have to fill in the other things. Sometimes they would give you the center and then they would give you a minimum and then they'd want you to find the maximum. So we'll look at some different examples that they do that. I think it shows up on the homework. When the density is constant over an interval, the probability is called a uniform distribution. One thing I do want to do, because it doesn't show it in the PowerPoint, I do want to calculate the mean and the standard deviation. So mean is just the average, so a plus b over 2. And you can write all this out if you want, but it's just your middle point. So it's always your midpoint. So 5 minutes is my mean. And my standard deviation, I'm going to take the square root of my range, which is 2 over 12. So the square root of 1/6, and I don't know what that is. Somebody type that in and tell me. Oh, it's actually 2 squared.
1 over 2.2.
Hold on, I was wrong.
That's what it does.
It would be square root of 4 over 12. So square root of 1/3.
0.574.
0.574.
Something like that.
Really? Did you
It's
come with that in your head?
0.577.
0.577. Okay. Did you do that in your head?
No.
Oh. I was about to be really impressed. I was like,
I
whoa.
was 0.09 off.
0.577. So, a couple things to remember on a uniform distribution. That your mean is always your midpoint. Your height can be calculated by doing 1 over the range. Sometimes questions will only give you so I'm just going to make up an example because I don't know why it's not on the PowerPoint. So let's say that they give you a question that's a continuous distribution of time, and they give you the mean is 10 minutes, and then they give you the max time is 14 minutes. And then they ask you for the probability that's not how you spell it. I don't know what I did. That's not right. Probability. There we go. Probability that x is less than or equal to 8. And then they tell me that it's a uniform distribution, or it's even. So my first step, if I were answering a question like this, you might just want to write this out to the side. My first step when I'm answering a question like this is you always draw your x-axis. It says that my mean or my midpoint is 10, and then I have a max at 14. So then I need to draw in what my minimum would be. And what would my minimum be? 6. Because it's an equal distance away. Then I have my rectangle like this. Then I need to draw my height. My height is always 1 over the range. My range is what? 8. Then it asks me for the probability less than or equal to 8. So it's this shaded area right here. And my probability is always base times height. This is 8. My base is 2. My height is 1/8. So my probability would be 1/4 or 25%. So on uniform distribution questions, they usually make you draw it yourself. They don't give you a picture. I rarely see pictures on uniform. The biggest mistake I see people make is that they treat it like it's a normal distribution because they didn't read the word uniform. So anytime you're reading a scenario, always make sure, be very careful that you read what type of distribution it is. So if it says uniform, you're going to draw something like this. If it says normal, then you're going to do stuff in the calculator. That's my biggest piece of advice. Other density curves, we're not going to do any crazy calculus or anything like that. We won't be finding integrals. You might see something like that if you have to take a college stats course. But the only other type of density curve that we will look at will be a normal curve. I'm going to skip that. So mean for a continuous distribution is always the center. And the standard deviation is the spread. That's kind of like review of stuff we've already talked about. Okay, let's look at, so we're going to start talking about what it looks like to be a normal curve. So a company receives concrete of a certain type from 2 different suppliers. So we have compression strength from supplier 1, compression strength
So it's supposed to be a 2.
from 2. It should be 2. I don't know why it says 1. There's a typo. And we have 2 means and 2 standard deviations. The first supplier is preferred to the second, both in terms of mean and standard deviation, or of variability. So if I were to graph the distribution for the first supplier, it would look something like this. If I were to graph it for the second supplier, it would look something like this. So the mean is smaller, but the standard deviation for y is bigger. So this is just kind of review of what the normal curve looks like. Remember that mean, if it's higher, it's shifted to the right. If my mean is smaller, it's shifted to the left. So the mean for x is going to be somewhere here. Mean of y is here. But then also, my standard deviation is correlated with the range. So if it's more spread out, it's going to have a larger standard deviation. If it's more compact, it's going to have a smaller standard deviation. Remember talking about, well, I guess this is a different example. Wolf Grocery had a total of 14 employees. It gives us the salaries. How would I go about finding the mean and standard deviation of something like this?
Or just put it in the calculator.
Put them in the calculator. So just do a list. And then I could do 1 bar stats, get my mean and standard deviation. Is this a population or a sample?
Sample.
Actually, it's
Wait.
population.
Total employees.
Total employees. So it gives me all 14 employees. And then it gives me the standard deviation. So I'd want to use sigma if I were doing 1 bar stats.
So which is X the top row, or does it not matter?
It's all.
No, it's all just 1. So it would all go in list 1. Because it's 14 employees. It didn't give me 2 sets of data. If I gave everyone a $100 raise, what would the mean and standard deviation be now?
The mean would
stay
the
the
mean would stay
same.
the same. No, the mean would go up, and the standard deviation would be the same.
The mean would go up to
Oh, yeah.
1,800, and then standard deviation would stay the same. So just like, if you've noticed, we have done this linear transformation concept in 3 different chapters now, where you're like adding, subtracting, multiplying, dividing. So make sure this shows up. It showed up in the last chapter. It shows up in this chapter. It does not go away. We keep with this concept over and over. So remember, if you add, subtract, multiply, divide, that changes your mean. But if you just add and subtract, that doesn't change your standard deviation. The only time standard deviation changes is with multiplying, dividing. So that's kind of what it looks like with the 2 different salaries. The first one with the $1,700, and then the second one with the raise of $100. Spread is the same. If we deducted everyone $100, then it would be $100 less. What if we gave everyone a 20% raise? What would I do? I would multiply the mean and the standard deviation by what?
1.2.
1.2. Good. Yes. So when I multiply by 1.2, that increased the spread. That's the 3rd box plot, just to kind of show you the concept. But I think this is all review, so we should be good with that kind of thing. A normal distribution. We have talked a little bit about this in Unit 2. We've also done some of the calculator stuff, so a lot of this will be review. I think you'll really like it. It is a bell shape. It's always centered at the mean, and it goes out within standard deviations. The area under the curve always equals 1. To find the probability, you do the area underneath the curve. How is this done mathematically? Well, you would probably need to use an integral function by hand, but if we're doing it in the calculator, we would use, does anyone remember what calculator function we used?
For what?
Second bar stats.
No, to find the area under a normal curve. Remember when we did the empirical rule?
Is this the plot thing? Or we
Yeah.
did the y
Residuals.
residuals?
No, this is when we did the normal CDF.
Oh, what?
Y'all remember that?
Second stat, right?
What is normal
Going all the way
PDF?
to the right?
We don't ever use normal PDF. Never, ever, ever, ever. Because it would always equal 0. It's like saying exactly.
Is that
So
the
that's like the
thing?
line segment thing.
Oh.
Wait, so if it always equals 0, then why is it doing that?
I don't know.
For people who don't
You
know
should ask
the
Texas
advanced things we
Instruments.
know.
You should ask Texas Instruments.
Really should.
So we would use normal CDF. As your standard deviation increases, the curve flattens and spreads out, kind of like the picture. As it decreases, it gets taller and thinner. So these are just two conceptual concepts that you need to know. But I think that it's pretty self-explanatory. Do these two have the same mean?
Yes.
Yes?
5. Or whatever, I don't know.
I think it's 6. Yeah. Which one has a standard deviation of 3? Remember
A.
that standard deviations, how many standard deviations does a normal curve go out on each side?
Is it 4? Or is it 3?
3, about 3. So
So then B.
the standard deviation of A, if I'm going out 3, is about 1. And then the standard deviation for B, you count out 1, 2, 3, 4, 5, 6. Might even go a little bit further, maybe.
Okay, so what do we need to know those numbers again? Like 78%, 90? I don't remember what it is.
Yeah,
78,
68.
68.
Yeah, we'll go over that here in a minute. So the main concept is when you're looking at a normal curve, you want to take the distance from your mean to the outside and divide that by 3. And that's about your standard deviation. Or you could take the range and divide it by 6. Because remember, from the distance from the mean to the outside is always about 3 standard deviations. So notice that the normal curve is curving downward from the center, 1 standard deviation on either side, and then it begins to turn upward after 1 standard deviation. Okay. This right here, so once you go out 1 standard deviation, this is called like a point of inflection. Sometimes I've seen the AP test talk about it like once or twice. That should be inflection. And that just means it's like changing directions. So it's pointing downward and then it begins pointing kind of upward again after 1 standard deviation away. It's not a huge deal. I just have seen it asked once or twice on the AP test. The empirical rule, you got 68, 95, 99.7. You do need to memorize those numbers, but like I said, the calculator does do area under the curve for you. The standard normal distribution, so anytime I say something like the standard normal curve, it is when your mean is 0 and your standard deviation is 1. And every single number on that represents a z-score. So all of these numbers right here are z-scores. And that goes back to when I talk about the standard normal distribution. So anytime that you find a z-score, does anyone remember the formula for z-score?
Pretty simple.
Simple? Oh.
Pretty simple. So you take your x value minus the mean over the standard deviation. You do need to memorize this.
How do you know that was a z-score? Because it said z-curve.
How do I know this is z-score? Because anytime you have a mean of 0 and a standard deviation of 1, that's a z-curve or a standard normal.
And did you know it was a standard deviation of 1 because that's what it's counting by?
Yeah. That's what it's counting by. So any distribution with a mean of 0, standard deviation of 1 is called a standard normal, and it represents z-scores to the left and to the right. I'm going to show you guys the table later. I don't want to confuse you with the table just yet. I'm going to show you all the calculator stuff first, and then we'll go back to the table. Okay, so here we have a standard normal curve, and it says, suppose that we're interested in the probability that Z star, which Z star is the same thing as a Z score. Like, so the probability that your Z score is less than negative 1.62. I'm gonna skip. This is all on the formula chart, but I'm gonna show you how to do it in your calculator. So in your calculator, I want you to get that out. I want you to go to second vars. So in your calculator, you're gonna go to second vars, and you're gonna calculate the lower and upper bound. So my suggestion is that you always draw a picture because you're knowing whether you're going to negative infinity or positive infinity. In this case, my lower bound is negative infinity. How do I represent negative infinity on the calculator?
Negative 1 to the 99th power.
Not negative 1,
-2.
negative 2 to the 99th power.
Where are you typing?
Why does mine say negative?
Why is
one?
it 2?
It could have an E.
Wait,
Does it have negative 1 E99? That's like saying, so if you have this, it's like saying times 10 to the 99th power.
we
Oh,
have
really?
We haven't gone there.
So you go to second
Wait, so it is fine to use the
vars. If you have the E.
Okay.
So you're going to do normal CDF. My lower bound is, I'm going to say negative 2 to the 99th. Any really, really, really small, or I guess really big, but negative number. Negative infinity. Then my upper bound, I'm going to stop at negative 1.62. Then I'm going to put in my mean and my standard deviation. My mean is 0, my standard deviation is 1. Because anytime I'm talking about a standard normal, or they give me a z-score, then it's represented by 0 and 1. Then I hit paste, and you should get 0.0526.
Got 0.94.
Did you put negative 1.62, or did you do positive 1.62?
I did positive.
Okay, it needs to be negative 1.62. So when I show you I prefer doing the calculator for everything. But in a minute, I'm going to pass out the formula charts. There is a table on the back, and you can actually look up, there's a z-score table on the back, and it gives you the area to the left. So if I were to use the table, I'm going to go down to the row negative 1.6. You can kind of see it on the PowerPoint slide. And then I'm going to go to the right to 0.02. And so that would be negative 1.62. And it gives me the probability it gives me 0.0526. You can kind of locate that.
What does the 0.02 represent again?
The 100th place. So if my z-score is negative 1.62, I have to go to the 0.02 column because that's the 100th place. So you go down to 1.6 and then over to 0.02 because that represents the 100th place. And the probabilities in this table represent less than or equal to. So let's say that it said greater than or equal to 1.62, I'd need to do 1 minus that number. So you can really choose whichever one you want to do. You can do this table or you can do the calculator. I normally prefer the calculator because it's just easier for me, but it is totally up to you.
Can you repeat what those first two numbers meant?
The lower bound and the upper bound. So negative infinity to, my lower bound is negative infinity because it goes all the way to the left. My upper bound, it stops at negative 1.62. Okay, less than 2.31. So on the table, I'm going to go to 2.3. Then I'm going to go up to, or I'm going to go over to 0.01. And you should get 0.9896. If I wanted to do that in my calculator, that would look like normal CDF. You don't have to actually do this if you don't want to. My lower bound would be what?
-2.
My upper bound would be at,
2.3.
and then my mean is 0. My standard deviation is 1.
So Ms. Thornhill, what's the number? What is this?
That's each number, like in the table, represents the probability to the left.
So less than?
So if you had a greater than, you would do 1 minus that, which I think we're going to do 1 in here in a minute. Anyone know what time the bell rings? 50. Okay.
Actually, 32. Also, maybe that
32.
number, which is
32.
actually like 35, 45.
Okay, greater than 2.31, that's where you'd have to do 1 minus that. Because the table only gives the area to the left. To find the area to the right, I would subtract from 1. However, if I were doing it in my calculator, you don't need to do, so normal CDFs, you never have to do 1 minus, which is actually very nice and handy because you don't have to do the 1 minus. I would just say normal CDF, and I would change my lower and upper bound. So my lower bound would be what in this case?
2.31.
And my upper bound would be positive infinity. So 2 to the 99th. So if you want, when you draw these pictures, you could put negative 2 to the 99th on the left and 2 to the 99th on the right. And that helps you determine like positive or negative infinity. And then my mean is still 0, my standard deviation is still 1. So if you want later on, you can go and check these in your calculator if you want. Okay, now a different type of question. Suppose we're interested in finding the z-score for the smallest 2%. So now I'm not looking at the columns and the rows in my table. I'm actually looking inside the table, and I'm looking for the number what? 0.2? Smallest 2%. 0.02. So let's look at our table inside. And which one of those is closest to 0.02?
0.0.
Negative 2.05.
So really it's in between like negative 2.05 and negative 2.06. Does everyone see that in the table? So I'm just going to say the closest one is negative 2.05. If you said negative 2.055, that would also be correct. But a way that we could do this in our calculator, and if anyone remembers, remember we did normal CDF. What was the other calculator function that we did? Anyone remember when we did that unit 2, maybe 3? So I'm going to go to second vars.
Is it in from 1?
I'm going to go to second vars, and I'm going to go to inverse norm. Inverse norm. And you use inverse norm when they give a percentile. So when you're given a percentile and it's asking for a value. So inverse norm, I'm going to put in my percentile, which is 0.02. That's going to be my area. My mean is still 0, and my standard deviation is still 1. And you should get negative 2.0537. Even more exact than the table. But if you like the table, that's okay.
Do you have to not like the table? Or can we not use the table?
The only time, so the table is nice and easy right now because I'm only giving you z-scores. But later on, you're going to get examples where the mean and the standard deviation are not 0 and 1. So in order to use the table, you have to convert it using the z-score formula and then use the table. So it's like 2 steps. But if you didn't want to do the 2 steps, you could just use your calculator and not have to convert it to a z-score first.
That formula is how you convert to a z to make it a z-score one? Like any...
So to convert it to a z-score, you have to do x minus mu over sigma.
You do that to any...
Okay, the next one is largest 5%. So if I'm looking at the largest 5%, what number would I want to look for in my table?
0.05.
Not 0.05 because it's the largest 5%. 0.95. And so that's about 1.645-ish.
Yeah.
if I were doing this in the calculator, so inverse norm, what would my area be? What percentile am I looking at? 0.95, comma 0, comma 1. So you're looking at the 95th percentile. So if it says largest 5%, then you're going to look at the 95th percentile. So standard normal curves always have a mean of 0, a standard deviation of 1. To standardize, you have to use the z-score formula. So this is what I mean by, if you want to use the table, you've got to do 2 steps. You've got to standardize it first, then you've got to go to the table. So that's why sometimes I prefer using the calculator, because you don't have to necessarily standardize it first. Strategies for finding probabilities: write the probability statement, draw a picture, calculate the z-score. That's sometimes optional, so I'm going to put a star next to it, and this is sometimes optional. So these two are one option, or you could just use calculator. So I'm going to put use calc. You could either do steps 3 and 4, or you could just use the calculator. It is up to you. So, the lifetime of a certain type of battery is normally distributed with a mean of 200 hours and a standard deviation of 15. What proportion of these batteries can be expected to last less than 220 hours? So, yes. So my probability statement, lasting less than 220. If I were to draw a picture, it's going to be less than 220. My mean is 200. There are 2 ways I could solve this. I'm going to show you both ways. I'm going to show you both ways. I'm going to show you the long way first, and then I'm going to show you the shortcut way. And it's going to be up to you which one you choose. You'll probably choose a shortcut, but I want to show you how it works both ways. So the long way is calculating the z-score at 220. And so 220 is my x, mean is 200, standard deviation is 15. So to find my z-score, I'm going to do 220 minus 200 over 15. And I get a z-score of 1.3 repeating. So if my z-score is 1.33, let's do 3 decimal places, then I can use my little table and I can go to 1.33 and I can find that area. So if I go to 1.33, you get 0.9082. I could use the table. The second thing I could do is normal CDF. My lower bound would be negative infinity. My upper bound would be 1.33. I have a mean of 0, a standard deviation of 1. And I use 0 and 1 because I standardized it first. So when I do that, I get 0.9088. So I could do my table using this value. I could do normal CDF. Those are 2 ways. That's the long way to do it. Or the shortcut is, so I'm going to just draw a line. My second option, so this is option number 2, shortcut. I could just do normal CDF of negative infinity to 220. My mean is 200. My standard deviation is 15. So I want everybody to type this in your calculator. And you should get 0.9088. So option number 1 is to standardize first. So by standardizing, I mean find a z-score, then do the table or normal CDF. That's the long way. But I do want you to know how to do that. Second way, and this is the way that I prefer, is just putting in your value and the mean and the standard deviation that they give you straight from the problem. And it's only one step. Yes?
Why did you normal CDF on the first one?
I normal CDF'd using the z-score and then 0 and 1.
You can't just
But
use
you
the time.
could use the table. So I showed you two ways.
Okay.
You could do table or that. And then the second way is just doing normal CDF. You can't use the table without standardizing it first. So if you did more than 120, you would do 1 minus 0.9082 or 9088, whichever one you did from the calculator. If you wanted to do just the shortcut way, you could do normal CDF of 220 to infinity 215. And you should get 0.091. Okay, the next one, it says a lifetime of a certain type of battery is normally distributed with a mean of 200, standard deviation of 15. How long must the battery last to be in the top 5%? So now it's asking me for a value, top 5%. So let's do this the inverse norm way. If it's top 5%, what percentile am I going to go to? If I've got a normal curve, the top 5% would be at the 95th percentile. So I'm going to do inverse norm of 0.95. My mean is 200. My standard deviation is 15. And what do you end up getting?
224.6728.
224 point something.
672.
So if it gives you a percentile and it asks for a value, you're going to use inverse norm. This is the shortcut way. That's the way that I prefer. On the PowerPoint, it does show you the long way. So what you could do is go to your table and find out what the z-score is for the 95th percentile. So that's when you're like looking inside the table and you go to 0.95 and then you go and you scroll to what the z-score is. So when you look up in the table the 0.95 z-score, you get 1.645, and then you solve backwards to find your x value. But that's the long way, in my opinion. I like the inverse norm way. Okay, the heights of the female students at East are normally distributed with a mean of 65. What is the standard deviation of this distribution if 18.5% of the female students are shorter than 63 inches? So this is an example where you have to use the long way. Okay? So it tells me that when your x value is 63, your probability is 0.185. So here's a nice little picture. So I want to figure out, okay, what is my z-score at the 18.5 percentile? 0.185. You can either use your table and go to 0.185 and see what the z-score is, or an even faster way to figure out to get a z-score is by doing inverse norm of 0.185, 0, and 1. So what this is doing right here is it's giving me the z-score at the 18.5th percentile. And I know it's giving me a z-score because I'm using 0 and 1. So somebody type that in and tell me what you get.
Negative
896. And if you look at your table, if you go to negative 0.89, you should see that you get about 0.185 as your area. So this is my z-score at 18.5%, and I'm trying to solve for the standard deviation, and it gives me the mean. So the z-score formula is z equals x minus mu over sigma. I have my z-score, negative 0.8965. I have my x value, which is 63. I have my mean is 65, but I don't know my standard deviation. So then, using algebra, I'm going to solve, going to multiply by standard deviation, divide by negative 0.8965. You should get 2 over negative 0.8965. And you end up getting something. You should get negative 2 over negative 0.8965.
2.231.
2.231. Let's see if that's right. Yeah, negative, or you should get like 2.22. If you're off by like a couple hundredths, that's the only difference is because I think this example used the table and then we are using the calculator, which is more precise. So table or calculator, you're going to be off a little bit, but I would accept either of them. Okay.